Hello, everyone. Today, we will be discussing protection heater. First, here is the table of contents. I will begin by discussing the basic concept of the protection heater, followed by an example of designing a protection heater, and then conclude the presentation. A protection heater is a heater used in a superconducting magnet to spread the normal zone when a quench occurs. The protection heater is one of the various protection mechanisms for superconducting magnets. For more information on protection mechanisms, please refer to Chapter 5.2.3. The circuit shown below is a superconducting magnet circuit that includes a protection heater. The photo on the right shows the actual circuit, with the arrow indicating the protection heater. The operating principle of the protection heater is as follows. If a quench occurs, a V-detect is generated due to the hot spot. For more details on this, please refer to Chapter 5.2.2. The generated V-detect is amplified through an amplifier. When the amplified value is compared to a specific reference voltage, Vref, and a higher value is measured, it activates a circuit composed of an IGBT. Through the circuit with the capacitor created by the switch, the energy stored in the capacitor is transferred to the protection heater, causing it to operate. I have previously explained the principle of the protection heater. Now, I will provide an example of designing a protection heater. This magnet is the MIT 0.5 Tesla 770 mm MGB2 demo magnet. The specifications of the magnet are as follows, and the target for protection is as outlined below. The MGB2 magnet operates in a semi-persistent mode with a current of over 100 amperes. Using an external heater, visible at the bottom of the photo, we will create a hot spot in the magnet to induce quench voltage detection. Additionally, the protection heater will be activated through capacitor firing, with the ultimate goal of keeping the maximum temperature of the magnet below 260 Kelvin. When the magnet is operating normally, the energy stored in the magnet is 1,800 joules. The enthalpy density of the superconducting wire needed for the calculations is provided, and the cross-sectional area of the wire is given as 0.055 square centimeters. Thus, we can calculate the minimum length of wire required to dissipate the internal energy of the magnet as enthalpy while keeping the temperature below 260 Kelvin. Specifically, if a 63-centimeter length of wire can share the current and absorb the heat, the magnet's temperature can be maintained below 260 Kelvin. Since we need to bring the 63-centimeter wire into a current-sharing state through the protection heater, we can calculate the energy required to achieve this state. Given that the current-sharing temperature of MGB2 is 30 Kelvin, it is calculated that 6.9 joules are needed to make the 63-centimeter wire share the current. Finally, we need to determine the capacitor's capacity, which can be calculated simply by charging a 25 millifarad capacitor to 49 volts and using 6 meters of copper wire. A total of 30 joules of energy can be used for the heater. Since the magnet operates in liquid helium, this design provides more energy than the 6.9 joules calculated above. We present the experimental results after installing the design protection heater. In the graph on the right, the red line represents the results without operating the protection heater, while the blue line shows the results with the protection heater activated. It is evident that the temperature of the superconducting magnet significantly decreases when the protection heater is activated. The protection heater effectively prevents the temperature rise of the magnet, as demonstrated by the experimental data. In summary, A protection heater refers to a heater in a superconducting magnet that spreads the normal zone when a quench occurs. By spreading the normal zone, the protection heater can protect the superconducting magnet from rapid temperature increases. That concludes the presentation on protection heater. Thank you for watching.